Shall I summon people? Hello?
It takes a moment.
Hello?
There you go.
There we go. All right, Ian's here. We can get started. Hello? Oh. Do you want to come through? We can get started. People in the foyer. Yeah.
Hey guys, we're starting now.
Yeah, they must be back.
Do you guys have any plan to give us these slides or some coding?
Yeah, I think so. All the slides are being put up, right? Right? Yeah, my slides definitely are going up. We're putting up slides. Yeah.
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 So keep an eye on the mailing list and go just to show you this one. Is there a new projector manufacturing and ratings?
Is that better? Okay, well, I think I'm just going to get started. Josh knows this stuff anyway, so. Good morning, I'm Chris. I'm from Rian's. I'm one of the original coders on Faucet. Yeah, so I'm going to talk about why we've made it the way that it is, and what we're sort of thinking about doing in the future. I think it's quite long, so we may run out of time for questions, but I think later in the day we're doing the dev workshop. I think we're planning to have a Q&A with the main devs. So you can definitely ask me questions at that point. And the other thing is I built the slide deck so that with the idea that we could use it as a sort of temporary reference for people wanting to code on Faucet. So it's quite text heavy so that hopefully people can sort of look at the slides and get the general gist of things. So that's just a warning. All right, so first part is sort of the philosophy that we're trying to adhere to. So our goal with Faucet is to be the easiest production SDN controller in the world. It needs to be easy to deploy, easy to operate, easy for someone who wants to come along and add a feature, and easy for a network engineer to support. And like, I'm a network engineer, not a software developer, or at least that's sort of how I thought of myself when I started working on this. And so for me, it was important that a network engineer who doesn't have a great deal of software experience can come in, get familiar with the code, work out what's supposed to be happening, work out if something's going wrong, why it's going wrong, and also to contribute features. I mean, that's kind of the point of SDN, right? Is that people can define their networking software. So, I mean, that's why we went with Python, and a lot of the decisions are about making it really easy to get your head around. So, yeah, there's the why we went with Ryu, OpenFlow. It's pretty straightforward. We have the philosophy that we'll do what OpenFlow allows us. Sometimes that can be a bit of a pain. And yeah, we try to stick to the spec. And all the testing is all built against Open vSwitch. So it's not just the spec, it's also the parts of the spec that Open vSwitch supports. So if it's not an Open vSwitch, we can't really do it because we can't test it. But, above all, it's got to work, right? It's got to be something that this network engineer that is able to read the code and stuff would actually be willing to deploy in his network. So it's got to be reliable. They've got to be able to monitor it. It's got to, it's not a case of throw out all your network and bring in FAUCET. It's got to interoperate with their existing equipment. Right, so in order to make the code really easy to understand, we try to keep it small. We're trying to only stick to the basics of what you need. We're sort of, the things in the data plane that you need in order to be able to build a network on top of it. So it's, we give you a fib, we don't give you VRFs and such. And yeah, so that's keep the code execution path really easy to understand. And also, when something weird is happening in your network, you want to be sure that it's, the things that you don't want in your network. If you're only doing switching and you're not actually doing any layer 3, you don't want some sort of tendrils of the layer 3 code sneaking in and doing strange things to your layer 2 network. You want to be able to just go, this is what we're using, that's all I need to understand. Hopefully everything else is not going to impact things for me. But that being said, it's really hard to build a network without any protocols. So we've added a few, we're adding a few more. But one of the goals when we add these things is to keep them nice and modular so that if you're not using them, you don't have to worry about them. All right, so one of the goals of decoupling, your control plane and your data plane is that if your control plane dies, it doesn't break your network necessarily. So we use fail secure mode. This is an OpenFlow concept that means that when the controller goes away, the switch will just stay as it was and keep executing exactly as it had been. So essentially your controller can die, restart, whatever, you can upgrade it, and you shouldn't see much impact on your network. One thing that will happen is that all the MAC addresses you've learned will time out. So gradually your network will turn into a hub, your switch will turn into a hub, but that's over the course of 5 minutes. So, and it's better than it breaking entirely and not forwarding anything. Yeah, and if you want more reliability, then the idea is that you can just use 2 controllers. So at the moment, your mileage may vary. It's going to depend on the switch that you're using and how they're handling that case. And you may have to do a little bit of extra work to get that going at the moment. It's not probably going to work out of the box for you, but we're working on it. And if you really want to see that feature, then it's open source. You can totally dive in and fix it. Right, so with this idea that the controller is not necessarily reliable, what's going to happen is that we lose a lot of state, right? So if there's state that's persistent, then it's in the config file. And everything else that we learn in the network, we just assume that at any point we can lose it. If there's any question about are we still synchronized, or the controller restarts, then it's just going to start from scratch and relearn everything, or your next hop resolution and layer 2 learning. So a controller, every time you reload the controller, there will be an impact in forwarding behavior because you'll lose all the learn MAC addresses, but it's fairly minor. It learns that stuff pretty quickly. And yeah, I mean, if we could make an entirely stateless network, we would, because state is kind of, it's almost, if it's stateless, then it's pretty reliable, right? It's only when state can change, and unfortunately in the real world, state can change, that you actually have to worry about reliability. So yeah, we try to keep that to a minimum. So, and one of the other points I wanted to make is that when you have when you add a new feature and you invent some way to configure that in the configuration file, and then someone deploys that, if you ever want to change how that's configured, then you're going to break that person's network, right? Unless they're really paying attention, there's every chance they won't see that. They're going to wake up in the morning and say, "Oh, why is all of a sudden all my VLANs disappeared from my network?" That's not really something we want to do to people. But yeah, the thing about should is you can just substitute that for probably won't. Bear that in mind. Okay, so one of the important things about Faucet that is kind of the obvious criticism that you have is that when you separate your controller and your data plane, then there's more distance between them. There's sort of more, when you communicate on that, it's a longer, more complicated path. Right, and so that sort of, you can have this risk that you end up with too much on your control channel. So when you're getting network traffic and you're sending it along the control channel, remember that the control channel is the only thing you have that can say to your data plane, stop sending me all that traffic. So if it's overwhelmed, then you can't actually stop it sometimes. But unfortunately, the control plane does have to look at some packets. We've got to learn MAC addresses. We've got to resolve next hops. But we try to keep that to a minimum. So the control channel is rate limited, but it's rate limited at the controller. And I think this is because Open vSwitch is not supported by metering, I think. Does not support OpenFlow metering. That's correct. Yeah.
Coming in the next release.
Great. Because, yeah, ideally that would be done on the switch. Right. But then the way that, because a lot of protocols do actually involve getting network traffic and sending them to the controller, we need to be able to support that. And so what we'd like to do is effectively have a data plane port on the switch that goes directly to your controller server. So this is not going through the controller port. It does not need to take the slow path in Open vSwitch or touch the CPU on your device. It will just be forwarded out a port as though it was data, and that port will then connect to the controller. And then the controller can basically get as much traffic as it wants that way, because it's not actually impacting its ability to communicate with the switch that's on a separate channel. OpenFlow has this concept of auxiliary channels, which is similar, but they still involve sending the traffic through the switch CPU. And yeah, therefore, it's not actually necessarily going to solve the problem that we can see, right? You're still sharing a channel between your data plane control traffic and your actual control traffic. All right, so the test suite is pretty important to OpenFlow, to Faucet. This is what allows us to do our cyber RFPs. He's not paying attention. We have, yeah, the integration tests are pretty good. Quite often we call these unit tests. So I think we need to be a bit clearer about what we call those. So the integration tests are the mini net tests that you can run against your switch. We also have some unit tests, and the unit tests are just trying to test valve, or I'm not sure that we have any for gauge at all yet, but there should be some. Those need some improvement. So the integration tests, you're testing the whole system, uses Mininet. The focus is to get this like really thorough, so that when you do your cyber RFP, you plug in your switch, you can be actually really confident that it's going to do what you want. Problem with thoroughness is that it makes it really slow to run. It's around 30 minutes. We like to improve that, but I think the fact is that we're just going to keep adding more and more tests, and at some point, you know, we're just going to accept the fact that these are going to take a long time. Currently, we've got almost 8,000 lines of the integration tests, and we've got about 8,000 lines in the core code. It's pretty close. The core code's slightly ahead. I think there's every possibility that integration tests could actually surpass that. Then the unit tests, well, the problem with the integration tests is that when you're doing development, and every time you like write a line of code and then test it, that's half an hour. Now you can break it down a little bit, but they're still very slow. So the idea with the unit test is to have something that you can run really quickly, make it really easy to write, because the focus is just on, you know, helping development, not impeding it. But at the moment, these are these need work. They're not nearly, we don't have nearly enough coverage with the unit tests at the moment, and there's a bit of shonky code in there that makes developing them pretty difficult at times. All right, so then there's the plumbing, how this all fits together. All right, so there's two parts to Faucet. There's Faucet and there's Gauge. This is because monitoring and control are separate functions. So Faucet does your control, Gauge your monitoring, and theoretically Gauge can monitor any OpenFlow 1.3 application. I suspect I'm going to have need of writing it to support 1.0 to 1.5 at some point for my PhD. So that's not really of any benefit to Faucet, but that'll be an interesting thing, perhaps. And then within Faucet, we've got Faucet and Valve. So Valve is actually the original project that we had that was a 1.0 OpenFlow implementation that we just needed VLANs on a switch. So it was really quite trivial. And then when we made Faucet, we forked that, but it only did one data path. So the idea was Faucet would sort of do the Ryu interaction, because we were anticipating the fact that we might want to use a different controller other than Ryu in the future. Whereas Valve, it controls the forwarding logic for one data path. And it uses the Ryu lib, but otherwise it doesn't really have much interaction with Ryu. Right, and then on the Gauge side, we've got a similar concept. So we've got the Watcher, which is, this is one of those situations where you've got this metaphor of a Faucet, and then you try to stretch it, and you eventually come to a point where it no longer works, and that's why it's called a Watcher. The idea that this is the person watching the Gauge, it's a bad name. Anyway, it's a similar structure, right? So Gauge interacts with Ryu. Watcher, I believe, has a little bit more interaction with Ryu, but it is the logic for monitoring a single statistic on a single data path. So there's actually, this is a little bit different to how it looks in the config, where you define a Watcher for, and you can give it a number of data paths, but what happens internally is that it builds a Watcher object for each of those. Right, and then the pipeline. So I think Ben actually went through this pretty well. So just to refresh your memory, port ACL, this is ACLs on a port by port basis. Then the VLAN table will assign VLANs according, check that your packet is correctly tagged, and then assign any VLAN tags on access ports. The VLAN ACL tables, so you can have ACLs per VLAN, the VLAN table can either forward it to there, or if the VLAN has no ACLs, it will send it directly to the Ethernet source table. Ethernet source table is for identifying packets that are where we've already learned the Ethernet source address. So if we haven't already learned the Ethernet source address, it'll send it to the controller and forward it on to the next table. If we have learned the Ethernet source address, then we just forward it on to the next table. So this table is quite overloaded. It does a few other things. It identifies packets addressed to the MAC address of any router that we have on that VLAN, and it will send those to the FIB. It sends up to the VIP table. It also filters out some bogon packets, things we don't want to forward, like CDP, LLDP, spanning tree, I think, and anything with a broadcast source, which should probably be a multicast source, but we just haven't done that yet. And yeah, it goes on. The V4 FIB and the V6 FIB, pretty self-explanatory. The key thing about them is that they do not, they don't output. They instead send it to the Ethernet destination table, which does all the outputting. The VIP table, this is for packets directed to the control plane, so it will filter those pretty heavily, and either allow them through to the control plane or not. And then the Ethernet destination table, obviously, for the MAC addresses that we've learned, it outputs them if we know them. Otherwise, it'll send them onto the flood table, and then the flood table has a whole stack of rules for forwarding packets. So a couple of things. So there's one of the challenges that we have is synchronizing the Ethernet source and the Ethernet destination tables. Unfortunately, they're in a separate table, and we can get into trouble when these two things get out of sync. So that's something we do have to be very aware of. And then the flood table, as been pointed out yesterday, that could actually be tidied up a bit. I think, you know, there's been, it's suggested that there's a bit of ambiguity about what the forwarding behavior should be when you try to forward a packet out the port that it arrived on, but I think the intention in the OpenFlow specification is pretty clear that you should not do that. But we have some vendors that do, so we've worked around that. It's not a huge deal, but I think it would be a bit tidier to do it with just one rule per VLAN as opposed to one rule per VLAN. And then some of the ideas for the future of things that we'd like to work on. As I mentioned before, yeah, the high availability is, I believe you could make it work at the moment, but I believe it should be easier to make it work. So the ideal for me would be that the switch just talks to one of its controllers, and then when it can no longer talk to that one, it flips over and talks to the other one. So it can do this as a, I'm going to talk to you and send you all the information that I need, but I'm going to ignore all of your commands. Or it could even just do it as a, I don't connect to you at all until this one fails, and then I'll connect to you. That would be great. That would work really well with the faucet model, but unfortunately, the spec says that the controller should tell the switch who is master, not vice versa, which makes the whole process, I think, a whole lot more difficult. But that's something I think we'll have to live with. Yeah, an API. So this is something we kind of, people talk about a lot, but we haven't really come to much of a consensus about how we should be doing this. So one of the key is that we don't introduce this whole new class of state of what are we talking to northbound? Is it still there? What has that said to us? Are we synchronized with that? I mean, my vague feeling at the moment is that you know, when you send anything northward, it's information and you broadcast it to everyone. So everything north of you has the same viewpoint, and then anything that comes southbound is a command and it's idempotent. And by that I mean when you get, like, if you've got 5 of these commands, they would be exactly the same, and you would do the first one and ignore all the following ones because it would be telling you to do exactly the same thing. So imagine the difference between increase this number by 1 or set this number to 3, right? If you increase it by 1 and you get the command 5 times, you end up with 8 or some other thing. Whereas, you know, if it's set it to 3 and you get that 5 times, it's set to 3. You'll still need to probably choose a master out of those, but it shouldn't really make a difference. Yeah, because your controllers, well, or everything northbound of you should effectively have the same viewpoint and should agree, but again, probably won't. And then virtualization. Pointed out yesterday again that our routing per VLAN is not especially efficient, and we'd like to move to using metadata internally to do some of this classification rather than using VLANs, which is what we're doing at the moment. Yeah. All right, I got through that fairly quickly. All right, so that's the core part of my presentation. I have about 20 bonus slides, but I think I might come back to those later since we're running a bit late already. Yeah, and I think for questions, we have the developer Q&A later on, and I think that would be a good time to do that. All right, thank you.
While you're still up there,
Yeah.
I would like to say thank you.
Oh, thanks.
And your observation, I understand why you chafe at 30 minutes as a long time for tests to run.
Yeah. Yeah.
I compare it to 6 months.
Yeah.
Thank you.
It's not so much chafing. It's just that when it's not, you know, yeah, you know, it is there for one reason, and then we need tests for the other reason, which is developing.
So your dichotomy of integration versus unit testing is spot on.
Yeah.
Integration tests should take as long as they need to take.
For sure. All right. Thank you.
Yeah, we have VGA only.
Yes,
and
there's the dongle.
That's good. Okay. That does have to be exactly. It's going to go through.
Is this good? Can people hear me?
Oh,
A little closer.
Yeah, you don't have much
Also,
screen
maybe
real estate.
turn it on.
Okay, let's just go.
Yeah, you're good.
Okay. Slideshow. No. Okay, we're good. Hi, I'm Atri Indiresan from Cisco Systems, and
Turn the microphone on.
oh,
It's on. It just may not be good. Try to.
It's arms. Just
which is it over here?
Oh, I see. Yes.
Okay.
I wear green colorblind, so I can't tell the difference.
yeah.
Here we go. Try that.
Okay.
There you go.
Good. Hi, I'm Atri Indiresan from Cisco Systems, and this is work I did with my colleagues Mel Sai and Manas Pati, who's in the audience over here. So just a very quick history. So till maybe about a year ago, we were, as Josh and Stephen will tell you, we were actively resisting the urge to do open flow, and then, we got religion, and here we are. So we wrote our first line of code around last December, and we participated in the Plug Fest in March, which went pretty well. So we made some progress. But how we got here was an interesting experience, and I'd like to share some of that. So I'm just going to talk a bit about Faucet versus OpenFlow. I think there's a good consensus over here, but I really want to focus this talk on what it takes to effectively implement a pipeline like Faucet in hardware in an efficient manner. So first, let's just say Faucet versus OpenFlow. I think for this audience, this is not controversial. So Faucet is a practical subset of OpenFlow, and I say this as a very positive thing. OpenFlow is many things to many people. It is incredibly flexible. I do believe it is more a software paradigm than a hardware paradigm, but what was done in Faucet really helped us define an efficient way of doing something useful. And to be honest, I'd say efforts like this or maybe other profiles are what could make OpenFlow effective. So let's dive straight into the pipeline. So first of all, let's look at a functional model, then we look at the implementation model. So what do we want to do? So baseline functions, Chris has been talking about these, which is a great lead-in talk. So we want to do L2, L3 forwarding. We want pretty good statistics. There's certain additional functions which are still pretty core. You want ACLs. You want to handle some protocols, maybe not all. You always need to punt to controller or someone with more intelligence. Monitoring, you can mirror the traffic, etc. Maybe in the future you want to do meters and tunnels. I know tunnels are not popular, but and they feel it's not necessary in this paradigm, but you never know. Okay, so you've all seen this kind of figure in multiple different places, and the diagram which Chris put up and which is on the Faucet website, it looks very similar. So now, again, this is an abstract model. What does it look like in reality? And when you look at the match action stage, they really mean a flexible match action stage. But the devil's in the details, right? So you come in, you parse the packet, and you do some intelligent stuff along the way, one after the other, and finally you go out. But it really doesn't say in your match action stage, what do you match against? Where are the tables? Are the tables tied directly to a particular stage, or is there some kind of a crossbar over there that you can access any memory from any stage? And these are very important design decisions when you're actually building an ASIC, because they might increase flexibility, reduce cost, whatever. There are different points in your decision. So let's look at, I think I spoke to this. The only other additional point I'd like to add is the rewriter. Do you want to modify the packet as you go through each flexible stage, or you want to do it at the end? So the logical abstraction in OpenFlow is that the rewrite happens immediately. But most hardware I have seen, they gather the rewrites, and then you have some kind of a rewrite engine at the end of the pipeline and make it happen. So, different ASICs do things different ways, but again, this is an implementation decision. But the logical abstraction over here is when you modify the packet in OpenFlow, it happens immediately, and that result is visible in the later pipeline stage. Transmitting, nothing much going on. You always have to send packets out. Okay, so let's look at the hardware resources. You want a programmable, flexible parser. Right now, it's just IPv4, IPv6, Ethernet, some layer 4 fields. Maybe in the future you want something more. But once you program your parser, you're done. You really don't need to mess with it too much. Maybe you want to. So it's good to have it programmable, but I don't want to spend too much time on it. The action really is in the middle part. So let me deal with the rewriter. So I think there is a value in being able to rewrite packets on the fly, especially if you want some more complex function, like I want to mirror a packet in the middle of the pipeline. So what am I going to mirror? the packet which came in, the packet which is going out, or what the packet looks like at that point of time. And this is a really, really hard problem to solve. And I think the way that it's been solved in Faucet is, we're going to mirror packets in the very first stage before any changes happen, so you've got the original packet. But in my conversations with Josh, he said, well, it could happen somewhere else. I hope not. I mean, we could figure it out, but it's hard. So just to make a point. But it's really the match action stages where all the action is. So I'm going to focus a lot more on the matching rather than the actions, but we can talk about that in the future as well. So we have different kinds of lookup tables. You can have TCAMs. You could have a special longest prefix match kind of hardware, hashes. These are really the common ones. You could have some simple tables, but the difference in cost between a hash and a regular linear table is not a whole lot. So yeah.
Sorry, maybe
Sure.
as a term of art, so the mirror in most of the industry, the mirror is quite a well understood term.
Sure.
But I guess another way to think of it is just a multiple output, because there may be, if you want to put some metadata on that packet for an external interface application to know about. So,
Correct.
yeah. So the mirror is the special case of data you didn't put any data on. It's really occasionally you may want to do multiple output.
Okay. Fair enough. And you just made the problem a little harder.
Yes.
He's very good at that.
I know. Okay. So, some rules. I had interesting conversations with Josh, and he sincerely felt that, okay, we tell you to do something and it should work magically without performance impact, and no, just do what we tell you. And he's very persuasive. And so we came up with an initial design, which was fairly performance impacting, and he emphasized the importance of doing it better, and we went back to the drawing board and we came up with a better design. So thank you, Josh. But having said that, here are the rules. Hardware resources are scarce, and flexibility can be expensive. So the more flexible you want to be, you have to pay a price somewhere. Hardware is definitely more rigid than software. If I want to redefine my pipeline in software, just put a new data structure and stick a new function over there, and magic, it just works. You've written the code in half an hour or a couple of hours or whatever it takes, and you define a new pipeline. Over here, somewhat more. TCAMs are our most flexible matching hardware, and they are significantly more expensive than hash. It's not even close in terms of scale and cost, real estate and the ASIC, everything. So if you don't use your resources efficiently and effectively, it could come down to even impacting functionality. There's certain things you just can't do because you've consumed too many resources doing something else. Obviously, you can impact performance if you spend too much time in hardware doing things in a complicated way, and scale as well. You, again, use too many resources, nothing's left for the other stuff. So we need to be respectful of this when we are designing a pipeline. These decisions are relatively easy when you have a fixed function pipeline. Say, oh, I need to do this over here. By the way, that match action stage pipeline I defined is exactly what a traditional pipeline looks like in an ASIC 10 years ago, except that they weren't very flexible. Today, we build them a lot more flexibly. But in a non-flexible one, you can put resources exactly where you want them. Oh, I want to put an L2 table over here and an L3 table over here and an ACL table. And it's completely fixed function. And you can make it happen very efficiently, but in a very rigid manner. So now let's look at what's in Faucet. And I want to state upfront, someone who works on the hardware side of these things, is we do have a problem. We have solutions. But there's a problem, and I think maybe they're better solutions. That's what I really want to talk about. Okay, so right now, Faucet has 9 or 8, which, depending which way you look at it, the V4, V6 fib are in parallel, and it's really an open question. Do we need more? Can we do with fewer? Are these stages a partial order or a total order? Now, this is a very, very important question, because already we see that there isn't a total order. V4 and V6 are in parallel. is it possible to take some of the other stages and break them up into multiple logical stages? And maybe the hardware has the capability, maybe it doesn't. And you can do certain things, like kind of a demux logic over there, and you can create different keys and do different things in parallel, or maybe actually you just select one path and do that. And that might be a more effective way of designing your pipeline. And the device driver looks at the logical model and says, oh, this is how I map it onto the hardware that I have. The other thing is recirculation is expensive. So every time you recirculate a packet through your pipeline, you are giving up, pretty much that full bandwidth, right? So let's say you could do something in one pass. You take 2 passes, then your packet forwarding rate drops 50%. Your line rate might not drop. It's just that now instead of doing line rate at 100-byte packets, now you're doing it at 200 bytes or whatever, which is not terrible. Our average packet size is probably closer to 500 bytes or more. So, but if you can avoid recirculation, I would say that's a good idea too. Okay, so let's dive in. And I'd like to talk a bit about how we actually went about designing our pipeline for Faucet. So I asked Josh, okay, so what do we have to do? Oh, look at the web page. It's all over there, cyber RFP, whatever. So yes. And we ran the simulation on Mininet, and we generated the logs of all the flows. And I wrote a few simple scripts, and it extracted every match action combination that was there in each table. So if you look at 1.3.2, this is what it looked like for the fifth table. In the beginning, we had an entry over there which looked at an ICMP packet and VLAN network source, network dest. Does that really belong in a fifth table? We didn't talk about it, but clearly they thought so too, and they moved it to the VIP table. And right now, in 167, it looks really clean. You're just looking at the VLAN and the destination. The one on top is really it's your catch-all entry. So that's fine. That's like a /0 address. So we are good. EtherDest, on the other hand, got a little bit worse, right? So it used to be very clean, VLAN and destination, and now suddenly you put in an import. So basically, I think this is what Chris was talking about a moment ago, that you need to be able to send the packet back out where it came from, because I looked at all the rules which did that, and they all did that. Come in on import, and your destination was import. So you're trying to force the packet back from where it came. So maybe it belongs in a different table if we can manage, just because I don't want to make, let's say, the more important tables complicated. So when I say they become complicated, here's the implication. If I have a very simple table with a fixed key, fixed width key, no mask, nothing, it's very easy to implement with a hash table. If I put in more variants of the key, I have to start looking at TCAN. And like I said in the beginning, TCAN's expensive. It doesn't scale very well. On our ASIC right now, we have implemented Faucet using only TCANs. And it's a frightful waste of resource. We have lots of hash tables in our ASIC, and if we can figure out a way of doing things efficiently, scale will improve just with some software changes. So that's an opportunity. It's good for everyone. Okay. I cannot overemphasize this. I don't like this. Okay. Chris talked about it. There are other tables. Please put it in port ACL, VLAN ACL, something, right? So when you have a kitchen sink, don't spread the kitchen sink throughout the house. It belongs in the kitchen, in the bathroom, wherever, right? Not throughout the house. This entry in green is only one. I mean, yesterday, I think in your talks, Stephen, you talked about, okay, source is a tuple. Import, VLAN, and source. Keep it that way. So if you can have a clean table, guess what? This is a hash table. Today, it's a TCAM. So, you want maybe 1,000, 2,000 MAC addresses. We're good. We've got enough TCAM to do something like that. But, you turn around and say, oh, I want to support 10,000, 20,000, whatever MAC addresses, and you put the same number in the destination table and in the source table, and guess what? Suddenly, the system just doesn't scale. So if we can change how we do things, life will get better. Okay? Okay. So, oh, absolutely. Anytime. Feel free. Oh, by the way, I'm deliberately being provocative, so feel free to shoot me down.
No, I don't want to shoot you down. I want to ask what you want.
Yeah.
So, sure, in some hypothetical other project that none of you have seen, I have a lot of tables, and we have a lot of these problems, I would say, in the tables. And as creator of the pipeline, from the top down, I recognize that I'm making a mess.
Yes.
Like, I get it.
Yeah.
What I want to do is I'm wondering, I don't want to give you the mess. I don't want to give the OpenFlow switch the mess. But if I'm going to give you really, unravel it, I'm going to hand you 55 tables.
Yeah.
Because I want to take every one of those sections.
Yeah.
And I want to make them their own little tiny table.
Okay.
But of course, I realize none of the hardware I have available today is going to support 55 tables.
Sure.
They're all going to go and die. And there's blocking sizes, and it's just never going to work. So we have this bizarre tension. I want to give you guys the hardware everything you have so that you can arrange it as optimally as you can get. But then I need assurances from all you hardware folks that if I give you 55 tables, if you're going to implement it before, that you'll do that behind my back, and all will be happy.
Okay.
If I have to look at a table like this and say, I'm going to guess for this hardware that one in green is the important one, and I'll take 2 kitchen sinks and make them on either side of that, and have a now I'm guessing what the hardware is going to be good at, and I'm probably going to guess well for the switch that's sitting in front of me.
Okay.
I'm probably going to guess poorly for the switch that I'm going to buy in 6 months.
Okay.
So can you guys do that? Can you take 55 tiny tables, tiny specified tables, and say, yeah, I'm going to throw those 4 into one kitchen sink?
So maybe to paraphrase my friend and colleague, so we have our creative teaching here.
Sure.
Right? So as you pointed out right at the beginning, it's like the ideal software world, which is ideal, and there's the ideal hardware world, which is also ideal.
Right.
We're just trying to discover where is the happy medium.
Sure. I mean, it is an interesting question, and let's put it this way: we have. I can't give away too much by way of trade secrets, but let's just say we have considerable amount of flexibility in our ASIC. So just to give you a little historical perspective, this ASIC first version was designed, 4 or 5 years ago. It was meant to do, a little bit of Ethernet switching, IP, some ACLs and stuff. And later someone said, guess what? We need GRE. We were able to do it. We need MPLS. MPLS was hard. We put an MPLS on the same ASIC. OpenFlow came along. This was not designed for OpenFlow, but we turned it around in a couple of months. VXLAN, we did VXLAN. So we have an ASIC which looks like fixed function. It's fairly flexible. I mean, people have seen what the barefoot architecture looks like. I'm not saying it's the same, but somewhere in that general vicinity. So if you give us a large number of tables, 55 seems a lot, but maybe, yeah, fair enough. But one of the things that we can do, remember I asked the question, is it a partial order or a total order? So if you can define these as a partial order and we have a clean demuxing function, at least on ours. So for example, in the fib table, I just check, is this packet V4 or V6? And so I'm going to form my key differently. Then I can actually decide which way the logic goes. It's an if selection. No, so it's not terribly hard. I'll reveal something. My boss is not here, but my job's not that hard, right? I've been developing software for so many years, and I can go months without writing a for loop, right? It's straight line code. You saw what that pipeline looked like. One after the next, and there's some selection logic in between. So I go somewhere, one to the next. So hardware forwarding of necessity needs to be simple, right? And that's the only way to make it really efficient. So if we can define partial orders such that you can just say that the longest path through this, and not just it's a partial order, that all of these stages are parallel and we have a clean way to distinguish the key. Okay, in the stage, if it's an ARC, I'll do this. If it's V4, if it is V6, maybe if it's ICMP, I can do different things. If I can make that decision in a very clean way, there is a good chance that I can separate them and form different keys and use different resources in the same stage, because I'm not doing all of them. Right now, I've decided to do all of them. I have a 512-bit wide TCAM, and I put every imaginable field, L2, L3, L4, your ports, whatever else you want over there, and it just magically works. It's a TCAM. Oh, I'm not matching in this. I mark that field. I don't care. Guess what? It's easy. It works, but it's not efficient. So that's why I said we can have this conversation, what kind of thing, and maybe you'll have a different conversation with a different vendor, because their hardware capabilities are different, and maybe they have a small number of processing stages and you have to keep recirculating to achieve the kind of things that you're talking about. And maybe we have fewer or we have more and we do things differently. So finally, you have to map it onto your ASIC. And this is also what Josh expressed to me. This is the functions that we have, and it doesn't really matter to us how you achieve it. That's the responsibility of the driver. But what I'm trying to say is, if you give us this kind of information, and maybe the driver can do something intelligent with it, and now I'll start writing slightly more complex code in my drivers. It's no longer straight line, simple graph traversal algorithms. I can still do these things. My brain's not yet fried.
By giving you this information,
yeah.
You mean table features, right?
It's table features, unfortunately, does not cleanly express concurrency.
I would like to discuss this with you offline in great detail.
We'd love that. So if there are enhancements to table features which express this concurrency in a nice way, it's something that we could use, which anyone could use, and maybe maybe a future ASIC we need to design to use this information better. But right now, I think we are at a point where I can say that I have begun to understand what Faucet looks like and what the requirements are and how we can do a good job with it. And that's what I'm trying to express over here.
So, well, number one, thank you very much.
Sure.
For the work. And actually, there's another observation. So there's different meanings of the word optimal.
Yes.
Right. So for us, the optimal flows are the ones that cause our business to work.
Yes.
And that may not be optimal in terms of, like, we may use more expensive hardware resources than possibly we could. But,
yeah.
But boss is happy, so it's good. So that doesn't.
So before you finish that thought, I just want to point out. Sure. When I started, the first thing I said, what's the functional abstraction? And then I said, what's the implementation abstraction? So I fully agree with you. If the device doesn't do what you want it to do, it's worthless. Right. So please go ahead.
Well, just so on that, I think in all the work that you've done, kind of this point is taken it where we can really use it. So
sure.
I really appreciate you engaging in this creative teaching, to get to this point, because sure. It's extremely helpful.
Thank you. Okay, so let me. Yeah, go ahead.
So what I've inferred from the way you described this is that if a given pipeline stage, if a given open flow table has one kind of match, you do it in a hash table. If it has more than one kind of match, it has to go to a TCAM. Is that, first, is that assumption?
That's a hardware-specific decision, and it's not a question of one kind of match versus multiple. If it is a fixed match, then you can do it in a hash. The moment you put in a mask, it's really, really hard to do it with a hash table.
Okay.
It is still possible, but it is incredibly hard.
These are not so different from the performance constraints in software, in fact. And so you showed a table with 8 kinds of match. And so in software, we would implement that by having 8 hash tables.
Yes.
And just running through all of them and picking the one with the highest priority.
Correct.
And so I wonder if you have the facility, the ability to simply use multiple hash tables for a given open flow table.
Yes and no. The problem is that we need to form the key. So if we have a selection logic ahead of doing the hash lookup, yes. But if it is hard to decide in advance how to form the key, then we really don't know what to look up. With a TCAM, life is so easy. You program the entry, and when I form the key, I just put everything in it. So if there is a selection logic for the keys, and if we have some way of expressing that, maybe as part of TFM or something else, then I would say it is easier. And again, like I said, I don't want to speak for all ASICs at all times, but what we have a certain degree of flexibility. And so the answer is yes, maybe. Okay.
All right, thank you.
So, yes.
Quick question. Are you having to develop your own silicon, or are the merchant silicon chips available good enough?
I don't believe there is much by way of merchant silicon which has this level of flexibility. I mean, clearly there's Barefoot out there. They're really new in the business. I have taken a look at some of their architecture. I think they have different kinds of constraints in the way they do things, but they seem to have done a pretty good job. I don't know enough about some of the more recent stuff which has come out of Broadcom. I do believe they're somewhat more constrained. The newer switching ASICs are more multi-function rather than flexible function. They put in a lot of functionality. Like I said, all the stuff I said we did in our ASIC and we just programmed it. Guess what? It's there in Broadcom, right? They have their VXLAN, they have MPLS, they have L2, L3, and the works. The difference is that we had a common reference architecture, and we were able to use software and drivers to make these things happen. So maybe if you squint hard enough, you could make some traditional pipeline work, but unless some flexibility has been built into it, it's hard. If you look at network processors, it's not a problem, right? It's obviously you can get the functionality because it's a CPU finally. Obviously, you have problems related to your scale and performance and so on, but you can do it in a network processor. But switching ASICs are significantly cheaper and more powerful as a rule than a network processor. So that's really where we want to go in the enterprise. I don't think people want to pay 5 times as much for an NPU-based system. Yes.
Yeah, I've got to respond to that because merchant silicon sitting out there, there's at least 3 chips that implement that pipeline unchanged.
Okay.
Fully featured.
Okay.
x86, we run it on that. Mellanox, we run it on that. We pass all the stuff. Barefoot, we run it on that at 6.5 terabits.
Sure.
Unchanged.
Sure. Barefoot is built this way. x86 is software, finally, right? So.
Yeah, but I mean,
yeah, fair
enough.
Yeah.
If you're under 80 gig, it's the perfect one.
Sure.
All of those have the same characteristics, that the mapping between OpenFlow and the specs and the pipeline that's implemented in the chip is very close.
Sure.
It's a one-to-one mapping. And yeah, 6 terabytes at Broadcom pricing Is it a penalty?
No, it's great. And the point I'm making is we also have the one-to-one mapping. I'm just saying that we have to make certain compromises in terms of how we scale these things, and we can make it better.
That part I absolutely agree with you. The open-flow pipeline designers have got to understand an exact match versus a wild-card match, what the cost of those.
Yes.
And code that into their tables.
Yes.
But beyond that, you can do a one-to-one mapping at very high functionality, very high flow table.
I agree.
Yeah.
I mean, if we can do it, like I said, there's no magic. If we can do it, someone else can do it too. So, just again, basic principles, what I've been talking about. If you can, fix keys for large-scale tables. So the most obvious one are source and desk MAC. These are fixed lookups. And if there's some MAC address with the mask, you can create a small side table and do something with that. You really aren't doing source IP lookups. If you want to do URPF, RPF, things like that, maybe. Desk IP, if you have host routes, especially in an enterprise, you're going to have mostly host routes. You can put those in a hash table. Longest prefix match, you can put in TCAM or some kind of radix tree structure, whatever the hardware supports. And again, you can optimize over there. And again, you can make narrower keys rather than wider keys, and that helps us as well. Struck out multicast. People here don't like multicast. That's fine. Let's not talk about it. So, yes.
There's nothing in OpenFlow that actually lets you express that what you're doing as long as prefix match.
No, it isn't. It is implicit, right? Because you just arrange the priorities in order of the length of the prefix match.
Right. So it's implicit. And I'm wondering for both you and all the other vendors in the room, as much as I hate to work, I'm sure people are going to hit me. If we had a canonical way of expressing that intent, not that it would break the spec if you didn't follow the canonical way, would it help people if we had used the canonical way? We'll do a better job of inferring that this is really a longest prefix match table if your priorities start on a power 2 boundary and always, I don't know if that would help or not. It's not a hard thing.
More information, let's say, it cannot hurt, right? Because then after that, it becomes a software problem. If once the information is there, if we have the hardware resources that can take advantage of it, it becomes a software problem.
Whether you can infer, oh, that's the longest prefix match table from the current stuff you're seeing, or whether you need more help to infer that.
We would probably need more help for that. I mean, right now, I look at it and say, oh, this is a FIP table. I know it's longest prefix match. I can do fun stuff with it. But,
until you get a flow that doesn't follow the pattern.
Yeah, then I'm in trouble, right? I mean, you decide that it would be nice to mask this IP addresses FF00, FF00. You could. Not sure why, but right.
The other comment I would just say is, I'm glad you have the functions listed in parentheses. Please remember, those may not be the functions we are implementing, even if those are the things we are matching.
Fair enough. No, that's what I said. I am talking of the major functions over here. So there are going to be plenty of other functions for which you need a lot of flexibility.
No. What I'm saying is that there are functions that have very specific and efficient use, but they aren't, and they're major for us.
Okay.
They aren't those ones.
Okay, fair enough. Point taken. Okay. And then yes, you'll always need flexible tables. Hopefully, they don't need to be very large. So there, you can put in L2, L3, L4 tables, whatever you want. We have single wide and double wide TCANs in our platform, which are 256 and 512 bits wide. So if there are only IPv4 fields, then 256 is good. 512 for IPv6. If you have a match which says, okay, on this VLAN, I'm interested in this TCP port. I don't know if it's v4, v6, and based on how I form the key, I may or may not need a double wide, especially if the IP field becomes optional. So I'm not too concerned about this because I think there probably won't be too many of them, and anyhow, I'm building a TCAM over there. So we definitely do want to leave flexibility at different points in the pipeline, but if we can constrain the flexibility, then life is good. Or better, right? So just what I've been talking about. So just how to be efficient, choose your keys wisely, respectfully. Then better pipeline stages. Again, we've been talking about that. You have more logical tables with distinct functions, at least distinct matching. If you have mutually exclusive packet types, then you can have parallel tables, so you have some kind of a demux logic at the beginning of your stage. If possible, limit rewrite in the pipeline stages. I know we can't always do that, but that's something to look into. Groups came in more recently. Guess what? I like groups. They're good. You know, it's you have shared adjacencies. Your updates are more efficient, and you can do fun stuff with groups. So, for example, oh, this rewrite happens, and especially if you've already decided your forwarding action, you can postpone the rewrite to the end of the pipeline, and you can do complicated things. Especially, let's say you want to introduce tunnels later. I think there's creative ways in which you can use groups, and not just question of efficiency. Oh, this interface failed. Do I need to reprogram all the flows, or just reprogram one group? Right. So that's a good thing. Okay. So conclusions, but this is not the end. I just want to start a conversation. Okay. So what are my intermediate conclusions? Building flexible pipelines is not necessarily easy. Fast, cheap, and flexible, as usual. You know, pick 2. Maybe we can get to 3 if we do things in slightly different ways. Maybe not a whole lot different. And you know, we have switch vendors, or application developers, end users, whatever. Let's talk and make the world a better place. Thank you. Yes, sir.
You seem to imply earlier on that it would be advantageous if once in one table you decided the packet is a certain type, with the next table it was easier to form hash key for it. So examples like once you decided it's IPv6, if the next table is only doing IPv6 matches, this is better, right?
The decision of what the packet type is typically made in the parser, right? So we carry that decision through the pipeline. So if we can use that information, yes, we can do things.
So the actual question that's going to follow here is, OpenFlow mandates certain preconditions in the type matches.
Correct,
The
yes.
preconditions, of course, make perfect sense.
Yes.
But they remove the potential for efficiency and size of hash key, because if you've already known because of an earlier stage the packet is v6, then the fact that you have to go up and add an ether type field matching to your silly match seems annoying, and in fact, at least in one particular switch, caused us to blow out the size of their hash table. Like, oops, it doesn't fit anymore because we have this dang prerequisite match. So my question is it reasonable to ask you folks to like say, can you infer that the prerequisite match is irrelevant, and therefore, even though I have to specify it, thank you, OpenFlow, you can like not bother to include that in the hash key?
Sure, it's not hard because again, that's software, right? So in the driver. So if you come and say, oh, this I'm going to match on IP. If I match on 0800, then I'm fine. It's just that if there is a possibility in that table that you might send me an ether type ABCD, then I still need to add those 16 bits. But as long as I know that I'm just going to match IP, I can just carry a single bit.
So now we just have to figure out and discuss how do we make sure that we know.
Correct. Yes.
So I'm loath to interrupt you because I love this. So I just wanted to, I think we have one, Ian wants to give a lightning talk. Is that kind of correct? So,
okay.
I'm okay, actually. Yep.
Are you sure?
Yep.
Okay. Does anyone else want to then steal his slots to do a lightning talk? Because I mean, if you...
I'm good. We can talk over lunch or anytime.
Okay. So I might then just declare morning tea then, I guess, and then we're going to come back and hear from Bill. Thank you very much.
So we talked to you guys a lot.
It's coming.
Thank you. So just before we start our next presentations, colleague Bill Fisher is going to talk about Forces and microservice. But before we do that, I want to thank two very important people, Kelly and Rebecca, for help make this whole event possible. It didn't help; they did make an event possible by causing you to have a building that doesn't fall over and has delicious food, and so you know where to go and who to talk to. So I just want to hear who our colleagues are, and if you wouldn't mind giving them a round of applause. Maybe you'll come to New Zealand next time. Maybe we'll come and bring you things.
That'll be up to Inder. So Inder wants to send us, we'll go. I'll do the travel.
Thank you.
Thank you.
Bill.
Right, can you hear me now? All right. So my name is Bill Fisher, and I'm an independent software developer in Arizona. And so in a past life, I developed software for network management, particularly using SNMP, the Simple Network Management Protocol. So today I'm going to talk about the Zoff framework that I created, and I'm going to talk about how it uses a C++ microservice underneath it called OFTR, OpenFlow Translator, which is basically the thing that does the work for Zoff, and Zoff is actually pretty small. I'm also going to talk about how I have ported Faucet to run on Zoff. Sort of Faucet is now hosted in Zoff instead of being hosted in Ryu. And I'm also going to mention how Faucet Test Suite helps me to develop Zoff, because without this, I would be basically flying blind and crashing into mountains. All right. So Zoff is the name of my Python OpenFlow framework. It lets you develop apps that use OpenFlow. It's open source, MIT license. It's an alternative to Ryu. I just want to mention that I don't actually use Ryu. I've never actually used it. I look at it a little bit because it's got a lot of I understand how the design of Ryu and POX work. They're event-driven frameworks. And one of the things I like about Ryu is their packet tests are pretty good. So I use those sort of privately. And I also want to mention that Zoff is not an acronym. It doesn't actually mean anything, and I hope it doesn't mean anything. And I tested this with a few American teenagers, and so far I think we're safe. All right, so this is sort of the data sheet thing. Now I buried the lead here. These are the bottom or the bold are my key differentiators. But the rest of the stuff is just sort of stuff I think it should do. So it's a Python OpenFlow framework with apps. Apps have handlers that can respond to events to OpenFlow messages. The framework dispatches the received OpenFlow messages to handlers, which may send OpenFlow messages in return. It supports OpenFlow 1.0 through 1.4 with partial support for 1.5. The 1.1 and 1.2 test, I don't think you'd want to use it because I don't think it's that well tested myself. You're probably going to use 1.3 or above. I support most of the OVS fixed length field names. And for stuff I don't support, like map fields, actions, instructions, it basically escapes to hex. So you can still code it if you know the right hex values for the field name, the field ID, and it's how many length bytes it has and all that stuff. Support TLS version 1.0 through 1.3. This is through boring SSL. It's capable of parsing, generating very limited number of protocols. ARP, IPv4, IPv6, TCP, UDP, LLDP. Did I mention? Oh yeah, ICMPv6, ICMPv4. Though the ICMPv6 support, you pretty much have to write most of the extensions because I don't do router advertisements or fun stuff like that. So I did that in Python. But if you want to produce a higher layer or something that is not supported, you have to bring your own parser or generator. So Zoff also supports the creation of apps that emulate switches, so support both sides of the protocol. And you can run them both in the same container, and they will go through the long path of making TCP connections to itself. And you can write an app that pretends to be a switch. And so I have a simulator demo that's in the framework. So let's get down to the meaty stuff here. Zoff uses async IO with async await. Async IO was introduced in Python 3.4. The keywords were introduced in Python 3.5, so I require Python 3.5. Now, Python 3.6 supports a little bit more, and it's at least 15% faster. So if you're using this, you want to use Python 3.6. So Zoff uses a C++ microservice that I wrote that handles the OpenFlow message parsing and construction, and it manages the TCP connections and the SSL state and all that stuff. So Zoff communicates with it using JSON RPC. It's actually technically YAML RPC because I have a YAML parser, but what the OFTR sends up is JSON so that it will be compatible with most programming languages. And the OpenFlow, the OFTR microservice gives you a declarative language to represent or construct any OpenFlow message, and I'll sort of explain, I'll do demos to show what that means. It's basically you write a YAML string and it parses it to OpenFlow. So here's a diagram of Faucet app running in Zoff. Notice I'm hosted in Zoff and it's not in Ryu. There's two parts to this diagram. We have this part over here, which is the software, and we have the test suite, which is basically the only way I have to make sure that it works. Because I do not have any hardware and I am pretty disconnected from everyone else. So the most amazing thing to me is that the test suite passes and I say here, and I'm like, you can try this now. And they're like, it works, great, I guess. So there's a Docker image you can try. We'll post that later. Let's see. So Zoff uses a separate program in C++ to handle the OF messaging. Right, so let's do an example. So switch 1 sends a packet in message to OFTR. OFTR translates the message to JSON and sends it to Zoff. Zoff parses the JSON message to a Python dictionary and dispatches it to each app's packet in handler. This is the slow path. An app handler can send OpenFlow messages in response. So what you send is what Zoff sends is a JSON YAML message to OFTR addressed to a particular switch. There's a data path. You can use data path ID or you can use a connection ID, which is something that I use internally to make sure it's actually going out the right connection. OFTR translates the JSON message to OpenFlow and sends it out the appropriate connection. So I ported Faucet to run on Zoff, and just so for non-programmers, porting means I make changes to the Faucet source code. So this is not a plugin replacement for Ryu, and I don't intend it to be. That has a different API. I tried to make some of the, when dealing with the packet data, I tried to make that API sort of match what Ryu does so that the packets handling stuff says, oh, I want a hop limit field. Just give me it on the object and it will get it, sort of using duck typing in Python. So my first check-in on Zoff was in about November 2016. This was before Faucet. I think I started messing around with Faucet in February, March because of the communications of the ACM article. And I saw the test and I said, wonder if I could make a framework and then I could test it by porting this thing on top of it and then reusing their unit tests because I like to reuse people's unit tests. At the time I had to make some changes to Faucet because you weren't Python 3 literate. So the end result is that Ryu doesn't need to be installed at all. And just to double down on the cyber RFP thing, I'm just a a lone guy. I'm a solo software developer. I have no networking hardware of my own, and I was flying blind. And basically, I think we can land with instruments. So that's good. This is just a blow up of that process, the soft process. So you can see that connections come in, we dispatch Python events as dictionaries. The way it works is there's one queue, and then this is 2 apps, and the apps get the event in serially. So that means that if faucet is first, then it can do something to like a features reply event. And then if the metrics app actually handled that, it would get it second. If the first app, these events are mutable. If the first app modified it, the second app would get the modified version. You can do something with exceptions to prevent other apps from getting events. This is it's very simple. And there are also state internal events like start, pre-flight, pre-start, which are things that the hosting container sends to apps to say, you're going to change state to do this thing now. And so there's a life cycle that an app goes through. So there's basically these message handlers, event handlers. So here are these channel up, channel down, features reply, packet in, port status, error, flow remove. Something about channel up and channel down. There are, in addition to all the OpenFlow messages, these are the 3 synthetic messages that I produce. So channel up says this is a data path, new data path is connected, and it has a data path ID, and we know what its ports are. And the ordering is that you always get a channel up before you get anything else. So what would happen normally is a channel up comes, and then you get the features reply, and then the port description reply, if you're listening for it. But it kind of bundles everything up. Channel down is when a switch goes away, and there's a third one called channel alert, which means it's a trap. It means you did either something happened that you need to know about, or or you can just ignore it. And part of it is you can make a programming error and try and send a message to something that doesn't exist, and you want to know about that because otherwise you wonder why nothing happened. Or you might want to know about OpenFlow packets that I can't parse, or there's a whole bunch. It's just a escape hatch for demons of stupidity. So this is single dispatch. This is just a quick list of the life cycle. Apps start in init state. They get a pre-flight event, then they go into pre-start, start, and stop, and post-flight. The 3 in the middle are async, so that means we've brought up the async event loop, and now you can do stuff like await for something else to happen. Pre-start is special because that's when the connection to OFTR is set up. I'm sending it the SSL certificates I want it to use. I am telling it to listen on these ports, and I don't want, you could have apps run concurrently like the metrics app does do pre-start, but you usually wait for start because that's when the connections are all set up. All right, so I just want to do some quick coding examples because I think this makes it actually a lot clearer what's happening. This is a complete Zoff program, and it shows the API. There's basically 3 main APIs you're going to use: Zoff application, Zoff compile, Zoff run, and then the thing returned by a Zoff compile has 3 methods on it, basically. So this is kind of like the web app frameworks in Python. I chose to use a roll request because this message, the first message, is pretty small. And so the way this works is you compile this YAML, and it has variables in it. So we got roll and generation ID. And what this will do is we can then, on a channel up event, send this message with these arguments. So if you run this, you just type Python and then 01 example.py, and because it's got this Zoff run here, it will just work. This particular app will require a greater than 1.0 version of OpenFlow. I'm sort of trying to remember when this was added. If you try to run this under 1.0, you would get an alert saying, I can't send that message because I don't know how. Now you'll notice that this is a send here. This is fire and forget. So we are not waiting for the response. If we wanted to, we could add a message handler for roll reply and do it that way. But what I'm going to show you is a better way to do this in another slide. Okay, now this is doing the exact same thing, but using a slightly different API. Before we were, we're parsing YAML, a YAML string, and this time we are compiling it here with this OF message thing, which is this thing returned by this function. And we're just generating a Python dictionary because sometimes it's easier to create dynamic things in Python code rather than trying to construct strings. And it does the exact same thing. Yeah, this is how I did the faucet port. So if you look at the faucet messages, they're all like this. And so this is a flowmon message. This is why I didn't start with this, because it's kind of complicated. We know we have a match, empty match, and instructions, apply actions, output to this port, and then down here we can fill in the variables. This message will work on all OpenFlow versions. It will backport it to the 1.0 syntax because it's not using anything. It's got one instruction that's apply actions, so it will work. And this is, it's a fire and forget still. This is the correct way to do a roll request. And this is now using async stuff. So we've got an async handler. We can get a reply from this roll request and print it. I'm going to start going faster. And here we're doing the same thing with a port stats request. In this case, we're going to pull it. So the channel comes up, and now we await the reply. Then we wait 5 seconds, and we keep doing it over and over again. Now, with async tasks, you can start a task, and it's very easy to forget that it is still running forever. So what this is actually tied to the data path that the event came in. So if the data path disconnects, this will actually get canceled automatically. Any other issue is here, you notice I'm not telling what data path ID to use or connection. I could do that, but implicitly it's going to use the one from the message that originated the handler. And this is a way to do a streaming reply if you're doing multi-part. You can use an async for loop, and it basically, you send the table features request, and then you can deal with the multiple replies. This is how I do fields in the syntax. The top one's kind of obvious, and then mask. And then there's the escape hatch where I don't understand what you are sending because I haven't added a name for the field yet. And then this is the same thing, but this is an experimenter field. I think it's an ONF experimenter field. And this is how you send a packet out. So you include the packet stuff in the message that you're sending. Basically, the fields are all set up. If you don't send a TTL, it will figure it out. But if you're using ICMPv6 neighbor discovery, you never set it to the right value, or else no one's going to accept your packet. So I was going to do a demo now, but I wanted to take questions because it's 20 minutes in, and no one's asking me. Does someone want me to do a demo, or?
So with all those dictionaries, I noticed are they just sensible defaults that you can ignore fields? Right, in the packet generation. Yeah, they'll default to all zeros. If you don't put an IPv source address in, it's all zeros currently.
it doesn't error on you in that particular case. Yeah, I was going to do a demo of showing, one of the issues with this language is if you input something and it's wrong, what happens? If you have a typo, if you misspell a field. So let's just do that quickly. No, this one. So I've got a little thing here that shows you. I'm just going to run through this quickly. Right, so you can use a Zoff codec to test the stuff, and what it does is it abuses the Python's codec mechanism to encode OpenFlow packets and then see what they look like. Right, so we can encode a features request just by telling this string to encode it. We can decode it again, and it comes out in sort of a canonical format. XID is also added implicitly by Zoff, so that's why you didn't see it in those messages. And then now I'm going to do what's called a round trip. I'm going to take my text, I'm going to encode it, and then I'm going to decode it to the canonical format because that sort of helps. Most people can't read hex, and it's not a great demo, so let's just do that. So we can encode, take this, and it converts into this. Take that, and we see that it's a pretty complicated message there. Most of the fields are zeros. There's a schema that helps you learn how this works, and it's in the OFTR command line tool. You type OFTR help flow mod, and it will dump out a schema that you can copy and paste and then just plug in values. There's a man page that explains just the schema that I'm using, which is just YAML, and it's the mail merge algorithm from Microsoft Word. So you just fill in the things that you need to do. So far, nothing is, something went wrong. I'm case sensitive. Row request has to be uppercase. I use the LLVM YAML-IO library, and it helps make nice error messages for things that are not perfect. So it's saying, do you mean that? We're missing a required key because we misspelled it. We have an unknown key, it's extra, it's not supposed to be there. Is it the same text? Yeah, it's the same text, but I replaced 1,000. Sometimes the constants, you can use integers instead of constants if it knows what it is, but it's going to try and figure out what the value is. That was probably a mistake in the slide. And you can use regular JSON. YAML is JSON. So let me just do this really quickly. So the tool is called OFTR. Right? So, oops. And it has its own help system. So, another way to do the encoding and decoding is it has, OFTR encode, and then, some YAML file, and you probably want to do -hex unless it's a terminal, because otherwise you get beeps. And there's an OFTR decode command, which takes binary files and converts them back to YAML, but it can also do PCAP files. Right, so I'm in a faucet sanity test from September when I was having some issues, so I had to copy it to my laptop, and the faucet tests have really good state to figure out what's going on, including packet captures and logs and things. But we can take that packet capture and decode it. And the first thing it's going to say is, no, I didn't find any packets because it's looking for 6653 or 6633. So I'm just going to tell it not to use a PCAP filter. You know, and it just dumps out everything. And if we want, we can get rid of the echo requests because they're annoying.
So much nicer than a t-shirt.
I hope so. So this is just glob syntax. Anything that begins with echo, exclude it. Or you can include, say, I only want the flow stuff, flow messages, or the packet in, well, the packet ins. I think I'm running out of time.
Yeah, please keep going. Yeah,
Okay. Let's see. So does anyone have any questions on Zoff or OFTR?
Well, I guess, I mean, there's a huge number of things here to like. I'm wondering, just as I'm trying to restrict myself to one question, is it, and we should have an offline conversation about it, but I'm wondering if there's a way that we can get your, to do some necessary trimming to get peripherals to speak to Zoff.
Right.
And I feel like we want to consider possibly having that as a permanent fixture in there. So
Sure. The shimming code is very small.
Right. Well, I mean, we want to get it in there, and then we can have maybe consider having multiple images. Like, do you want the review one, or do you want Zoff? It doesn't matter, of course. So that you can continue to do interesting Zoff things without having to maintain the shim.
Yeah, I mean, you aren't really modifying the shim that much anymore. So I mean, I'm happy with the way things are. The way I maintain this is I rebase on top of Faucet. So he puts out a release, and then I get rebase, which means I put all my patches on top of it. And that process has evolved pretty well. If you look, figure out how to get to, where am I? Over here. So I've got this, if you look at the GitHub repository for this, this is called branch port 5 because branch port 1, 2, 3, and 4 were previous things where I was not rebasing. So I'm pretty much solid on rebase. Any more questions? Let's go.
It wasn't clear to me during the packet in, is the internal packet, is that decoded?
Yes, sorry, yeah, that's decoded the same way as the packet out.
In OFTR?
In OFTR, and then it gets to JSON.
Okay, so if you want to support more protocols with deeper stuff, you send to OFTR. Well, you could take that.
You get the header that the last header I understand, and then I tell you the offset where I don't know anything beyond this point. So,
This is somebody who could send it. Oh, sorry.
well, do you want to, go 1, 2? Or do you want to go?
And then, as you mentioned, they don't have a lot of gear for testing for performance, but you have any idea of their performances?
Good question. So I knew I was speaking, I knew I would get that question. So I started performance enhancement testing like very recently. So the architecture here, it depends on what you're talking about with performance. Latency is going to be an issue because we got to go 2 hops. And I got to try and make it as fast as possible. Throughput might get better because we can parallelize. We've got OFTR doing stuff while the top layer is doing stuff. Turns out that when you do throughput testing, the bottleneck is the Python, and the OFTR layer is a lot faster. And what happens is, because I don't have flow control implemented, and OFTR buffers everything it is outputting to the upper layer, it gets stuck with a big buffer. And then the Python, when you stop the test, the Python code keeps processing all those packet ins till the buffer clears. And that's due to the bottleneck is the JSON deserialization in Python. So I'm thinking of switching that to a binary serialization using concise binary object representation, which is basically YAML, JSON, CBOR. They're all that ecosystem, that model of how to represent data. But that's where I am now.
things, yeah, so, gosh, so much good stuff. So maybe, one of the things that we have to do to take a lot of care of, in Fawcett is that, something turned up on our doorstep and you just got to deal with that. Another way to have something where we don't necessarily have to block, we can perhaps offload to Zoll saying, please help me protect from myself.
Right, rate limiting. I can do rate limiting at that layer very easily, or load shedding. Another thing that could potentially help is that Faucet does a lot of sort of mundane, boring stuff like answering ICMP echoes for virtual IPs that don't really require any state to do. You have to do it, but it's just work. Other things like, you don't do LLDP discovery, but that processing where you're continually doing stuff. The OFTR layer would know all the ports and know all the hardware MAC addresses if I added that. Right now it doesn't, it's stateless.
It would be fantastic that opportunity to say, for something that, like respond interpreters, it doesn't actually involve a change in the controller state, but something else can do that for us.
Right.
That does it state, that would be fantastic.
That would, so it would require programming in it. So it would be cherry picking the things that are the most important, I think, to start. That's how I would do it.
So, firstly, you're running Faucet. Are you doing Gauge as well?
Right. So I ported Gauge because I need the tests to work.
Right.
I also have in async IO, the way you're currently doing some things is somewhat dangerous in the sense that you are using some things that are blocking APIs, and that could potentially block my event loop. But if you're running Gauge separately, that's not an issue really. If you run Gauge, you don't recommend running Gauge and Faucet in the same Ryu instance, but I would like to have a metrics app that runs in Faucet that can do port information sort of on demand, and I've sort of made my own little thing. It's not quite compatible with Gauge, and it's sort of early stages.
And the other thing is just, so how much do you need to change Valve for this to work?
Change Faucet?
Valve and the Valve test.
Let's look at it.
Because the idea would be you shouldn't have to change the
I have to change valve.py just a little bit, just because my events look different from Ryu's. Let's just see what the comparisons are here. So I have my own little Docker stuff. Just as an, let's see. Oh yeah, I did not mention that I do support the pipeline stuff, but I use YAML instead.
Thank you for doing that.
And yeah, so the way this works is the idea is you can just read these YAML messages from a file, and you don't have to do anything. It will just send them. So if you need to send other messages, it's very easy to just update this file with the YAML that you want to send. There's a program that converts your JSON to this format. So that's just the same, more. And here's the program that does it. Yeah. So a lot of times I have to do things like this because I don't have Ryu installed, and I have my own constants that I use that map to the Ryu constants. So a lot of the changes are just one-line imports.
Theoretically, we could do this using the video and just convert that to Faucet into.
Yeah, like a Valve description that has a lot of stuff in it.
So here's the Valve file. I do pipeline a little differently. I have to get rid of the Ryu imports. This isn't, I use %R because it gives, these are JSON dictionaries. And yes, see, this is where I have to fix up things like Ethernet source and Ethernet dest. The Ryu API says source and dest. This is somewhat ambiguous in my mind, but.
So, theoretically, we could abstract all of this out and have like have Valve import Faucet away from the.
Right. Yep. Yeah, so the OF lib, when I get to that, we'll see all the changes are in val OF. There's just tons. It's so big that GitHub won't even display it. So
it's not technically.
Right. So any of these files that it's displaying are small changes. So it's fine.
Well, I guess we should talk more about this stuff. It's fantastic. Thank you.
Right. Thank you so much, Nick. So let me get disconnected here. Break the microphone. Is this yours? Thank you. So we haven't had enough New Zealanders recently. So our colleagues here from Victoria University, Michael and Ian, have talk about some NFV applications, including how to offload AO21X authentication using FAUCET. And some of the kind of neat stuff that I like about this particular project is it's been done in a way that can both interoperate with an older, non-SDN AAA, or you can go crazy and have your own if you like. Extremely practical. VGS HUD. It has to be exactly 1024.
Okay, I don't know how to change that. We'll find out.
Do you have a backup option?
We will do.
Okay.
What was it? 10?
Got to be 1024.
On?
Let's see what happens. Computer says no.
This is. You can switch to trunks if.
Yeah.
Oh.
The hardest part of SDN is the projector. So we will use a different machine.
What dongles is this here?
I think we've got the right ones. Great. Do you have the same presentation?
Oh, I'll have to download it again.
Okay.
No worries.
Do you want to switch the order?
That's a good idea.
Okay.
Yeah. So we can do that.
All right, cool.
Great idea. Thanks.
So SDN is very dynamic, so we're going to do a different presentation. So Tony's going to talk to us about scalable PE routers, if I remember.
Sure.
Hey, all right. Great.
I think I should have option to make it
Full screen?
Yeah. Okay. No.
Present. That's probably going to be how it is.
Yeah.
Sorry about that.
No.
Okay.
All right.
Here's your microphone.
Great. I need to turn this on. Okay. Control C F. All right. Yeah. So I'm Chung. I'm a student at Victoria University of Wellington, and in this talk, I'm going to talk about routing in ISP, and particularly, I'm going to look at routing scalability and so I just want to talk about routing in ISP, particularly like inter-domain routing scalability and the forwarding table scalability. And I want to show a simple approach that I think is very practical to deal with the scalable of the forwarding table. And I'm going to show how we can use SDN to realize a solution. So first, I'm going to discuss, what are the challenges regarding the scalabilities, and I want to show the next. I want to show how we can make it more scalable, and I want to discuss a reference for using SDN, and finally, I want to show how I use FAUCET to implement a prototype. And this is a picture of the internet. Internet routings. We have very beautiful pictures made available by Barrett, and each bubbles here represent an IS. And the high-level view, the very simple views can be shown in this diagram. And we have an ISP, ISPs, and enterprise customers, consumer users. In the talk, I want to look at the ISP, particularly the transit ISP. The basics are the primary services that ISP transit IP provides the transit service. Basically, they allow the customer to send the traffic across the network, and they get paid for that. And in order to do so, the ISP need to know every destination available in the internet, and they turn this into forwarding entries in their routers, and they also have to advertise the customer networks to the internet as well. And the only protocol that we use now for routings across areas is BGPs, and a version of BGP. So if we take a look at an ISP, we see the internal network is invisible from outside, and we can only see a number of app routers. And as I show here, we can see one routers have two main components. We have to control and data plane. So BGP is an ISP used with other IS. They learn the full BGP tables, and it's distributed to all the app routers across the network. And each router turn this into a forwarding table. From the customer point of view, we can see the packets into one X routers and get out the network from the other. And what we can see in this diagram, the same BGP tables typically have very identical destination prefix. It's duplicate as multiple app routers. That happened the same with the forwarding table. And for each packet, the IP lookup is done twice, at one app routers and at another app. Although they follow the same egress link. So I think we can make it simpler, when packets come in. Jeff?
I don't really understand this diagram. It looks like a full BGP table is connected to an ISP over two links, but enterprises are not connected to the ISP.
Yes, I think the missing link here, but it just represents a model. It's not like a physical link. What I mean here, an ISP have two sides. one side it connects with other ISP, and I can say this, we can call it the internet, whereas all the destinations are available there, and we learn the full table from there. And in one side, we connect to our customer, which have, each customer tends to have one network on it, one prefix. So the traffic's, going usually through one customer through the internet and the other direction. The ISP tend not to like transit traffic from one ISP to another. Yeah. So in this model, we have the traffic going from the bottom to the top and from top to bottom. There's no traffic, of course, within the top link. And yes, it's my mistake that I missed the link over there, but it just represents, how the routings and forwarding is done within an ISP. Yeah. Yeah. So as I said, like we can see when the packet is going through this network, we double the forwarding tables and the IP lookup as well. So what is the challenge? I don't know why we don't see the full. Yeah. So on the left-hand side, yeah, we see the BGP table structures over years since 2011, 2017. So it doubles every year, and at the moment we have around like 700 entries. And that means one thing, like the ISP need more bigger routers with larger TCAMs table, and it costs more. On the other side, the main service that they provide, the main income is transit service. It's declines almost 60% over the last 2 decades. So it's like one thing that I think ISP need a efficient solution but low cost, and in my opinion, SDN is the suitable replacement for the existing ways that they build the network using commodity hardware, which is, I think, is much cheaper than existing BGPs. So a quick look at the literature to see, how we can deal with the scalabilities of BGP and forwardings.
Sorry, please try to speak up as much as you can. Yeah.
You mean to louder?
Please speak louder.
Okay. Yeah. No, it's somehow like go down. Okay. Yeah.
Yeah, please speak louder.
Yes. Okay.
Thank you.
So a quick look at how we deal with, and a simple survey from literature, we see there are 2 different approaches that we are taking. One that we look into like how we can fundamentally change to the internet, and there's new protocols proposed, like for example the hybrid link state protocols, or we want to change how we are using address. We want to change addressing scheme, moving from IP to another, something that's more scalable and more can be aggregatable. The only difficulty with the approach that we don't know how to deploy it. Internet is too big that to any single providers and anybody to make a decision when we can switch to a new technology. The other approach seem more practical, with have some different options, like we can compress the table, make it smaller, and we can remove some unwanted prefixes. There's a drawbacks with one of these, like for compression, it's computational expensive. Filterings can cause connectivity issues, and for ISP they want to have more fine-grained controls. Like they want to see they can apply different policy for each different prefixes. So when we aggregate those prefixes together, we lost some control over it. So we want to see what can be other alternative. So yes, we take a look at this diagram again. We see, assume that we can divide the tables, the BGP tables, into a smaller one. And we say, okay, each router only keeps half of the tables on the portion of the table. And if we can program the network right to say the packets coming at one router and egress at another, and we say this packet has been processed, has been looked up already, so we don't need to do it as the egress router anymore. Yes, and in doing so, we can reduce the number of entries each routers have to maintain. And of course, we can, in a perfect world, we can double the scalabilities of the routing table. So this is show how it actually works. Assume we have this table, and it's very perfect to aggregate the prefix into two single tables. And if we say all packets belong to the first table going through this path, like S3, S5, and S, yes, and the others going through S4 and S6. So we can say the first router or switch only keeps one entries. The others, switch 3, for example, keep 2 other entries, and switch 5 2 other entries. So at the end, where the packets come in and go out at 2 different hosts out on the other side, we keep the same semantics of the full table. The packets either be dropped or be processed one of the entry. So this is how we want to do it. And we don't want like from the management point of view to see all those things happen. And so we want to introduce a concept like router abstraction. It's not something novel, but we say if the networks can be abstracted at a single router with a table that can be scalable, and all of these are invisible to a policy server or management, so we can realize those transparent to operators or to engineers' point of view. And we can do that with SDN. So if we put all those things together, so we can say an ISP, internal routings can be as a single router. But we don't want to be too optimistic. So we say instead of abstract the ISP as single routers, we can say we can do it at the port level first, because I think the latency between switches and the controllers can have a lot of performance issues. So an ISP where the ports located, as many different locations, the latency can be high. So it's not a practical way to abstract on the X routers at a single one. Instead of we say, okay, we do it at the port level, and and we can separate the two routing functions, which is the interrogating routings between the X routers, and within the X router, And we can use different controller, like for the one network between the port. There's another solution like SDN1, something like that. And those can be handled by 2 different controllers. And for inter-domain routings, we can introduce a new component like a policy server to handle routing between the ports and with the other ISP without knowing what inside a port. Yeah. So to support, like to study those things and see what can be the best way to decompose the tables and distribute the table to switches, we need a model, and I propose a very simple model with of forwarding tables which can be decomposed into very small one, and a set of paths between X routers and the capacity of decom for each switch, and then it's come with a set of constraints to make sure that the forwarding semantics is preserved, and then we can come out with a lot of other optimization problems, like we want to minimize the rule duplications, or we want to minimize the rule movement, like if the path chain, the last rule have to move from one path to another. So it can be multiple optimization of problems with this model. It looks simple, but I see there's some other challenges that we face. For example, the forwarding table is quite big, like 700,000 entries. And I see the simple way that we decompose by look through the tables and see which can be grouped together. It can take minutes at the moment. So we need a better way to do that. You know, if it takes a long time, we cannot deal with the rate of the tables updates. And in one day, we can have more than 100,000 entries updates. The table changes frequently. So we need to figure out how we can decompose the tables efficiently. and also, as the tables are update often, the algorithm cannot be static, which has to be online. And this is very simple one that I have implemented. It's not optimal, a lot of duplication, but we can see by finding the switch that share by multiple paths, we can install forwarding entries there, and then we reduce the duplication in the network. So far it works, but it needs a lot of optimization if we want to say if it's scale or not. And so I have something implemented using FAUCET, and the reason why, we have other options like SDN IP using ONOS or something similar, but the FAUCET, I think the best suit for this is because of the multiple tables, and it's very extensible, extendable, in my opinion. Like I can introduce new tables and without affecting existing features. And it's used Python, and it's good for prototypes. There's something that I need to train the FAUCET to realize that, for example, in a FAUCET routing is handled, individually by different veil. There's no concept of distributed routing abstraction at the moment, and we figure out the path from one switch to another using stacking, which is static. If the link fails, there's no way we can figure out that, and we can see the event that the link is not usable anymore. And we need some more APIs to see inside the networks. Like we don't know when a routing entry is resolved, and how we can program each switches differently. So this is the way that I did to realize distributed routing in FAUCET. It's not something major or important, like just use real frameworks to last values to see which routing events is interesting for the other values and broadcast it through the view framework, and the other can see that, so it can resolve its table. For example, in this case, we have 3 values with different forwarding tables, and a text came to the same host. I think the host one here is invisible somehow. So that traffic can go exists same host, but it maintains. It's not necessary that the host have to directly connected to one switch, and it works. I just don't know if the performance is good. And so this is showing how we can integrate everything to FAUCET. We have new components, which is I call it distributor, which handle the distribution of the tables, and it's received all the pass chains from the BSB speaker and make a decision where should the route store in those tables based on the stack topologies underneath here and the capacity of those switches. And finally, we have the full table in those data paths without any switch to store everything. And in terms of the pipelines, my intention is to use MPOS to tunnel. We need to tunnel packets from one data path to another. When the packet has been processed, by process I mean its headers has been rewritten to something suitable for forward to out the network, and MPOS is suitable for that. But that is on some hardware. It's not well supported. So instead, I use the stack import and the FAUCET source mark to see if this packet should be tunneled to other switches without going through the forwarding table. And there's not much has changed to the forwarding FAUCET pipeline. And it doesn't take much coding to realize the whole thing, like only a few hundred line codes for the distribution and a couple changes to FAUCET, and just so that's the end. Yep.
Questions that I just wanted to ask everyone to start with, because obviously we talked about this project before, but like the idea of a distributed router is like a great one to probably like explore how to do it. Because at the moment it's quite data path centric. So
Yeah.
it seems like it's be quite interesting to explore how to spread things out. Because there are several different ways to do it, so it'd be nice to support that engineering thing.
Yes, I think, yeah. Thank you.
So nice to hear. You guys are good together. Thank you.
Thank you.
Just download
Yep.
Have you got Wireshark?
Yes, I have everything here. So, okay. Work on it. Okay, I can open the WhatsApp for you. WhatsApp?
Okay, so we just do that.
Do you need anything else to run?
No,
Just
I just
Wi-Fi?
need Wireshark and internet.
I don't have internet.
Oh, no, we don't have the internet.
It's
Yeah.
only
Yeah, and you got yours?
it's for 2.4 gig, and there's no 2.4 gig over there.
Okay. Sorry about this.
So
Just get a USB.
now I can have internet over there.
Sorry about this.
Yes, it's ready.
It's ready. Thank you very much. Okay. Okay, Michael, we're good. Sweet.
Yeah, it's on the other side.
Okay, thanks. Okay. What's the phone version? Okay. Sorry about this. We're just got a laptop that doesn't do VGA. It seems. Or internet. We'll get to that.
Okay, you can't use Strong's.
Oh, it's also. He doesn't have internet on it. We can't
Okay.
connect to Wi-Fi.
Okay.
But we're just saving the file off onto a USB. Okay. Yes. Should we copy?
Do you want me to try and fix the internet?
Do you want? It's only 5 gigahertz. That's 2.4.
It's only 2?
Yeah.
Yeah.
Oh, you do?
Okay.
Okay. Cool. So. Am I typing? Okay. Yep. Let's move on here.
So are you downloading the presentation?
Yeah. Yeah, I'll download the presentation.
We'll just download it and then we'll just we're taking screenshots of it. Thanks. Okay, and then so it's home.
Mention it's home. Cool. Great. Drop that down. Yeah, because I can't see it. Okay, try. Tab. Okay. Maybe just minimize that. Chill screen. Okay. Cool. Right. Hey, I'm Michael. I'm going to be talking to you about 802.1x and Faucet. I drag this over on the mouse. Yeah, we're good.
Okay, cool.
Cool. So I've written an application for Faucet integrating 802.1x. So I can actually look here. So very briefly, 802.1x is a port-based network access control thing. So for port security, it's technically a framework, I guess, for EAP, and this EAP provides the different authentication methods of how you can authenticate. We can use it over wired or wireless networks and a few others. So basically, we have 3 main nodes. We have the supplicant, and that's one of it, which is basically a client, authenticator, which is a switch or an access point, and then we have an authentication server. No, I'm not using the mic, so am I loud enough? Cool. And we have an authentication server, which is our Radius server generally. Oh, yeah. Sorry. Is it on?
Yes.
Can you hear me?
Yes.
Sorry. So yeah. So what basically happens is the client sends a message, an EAPOL message to the switch then rewraps that message up into a radius message and sends it to the radius server. So a few of our design goals, what we've essentially done is with NFV 8021X, so we can process our 1X application stuff on a separate host from the switch. So our switch doesn't need to support 1X out of the box. We can use an OpenFlow switch, or if we want, we could use a dumb switch or something that supports VLANs, etc. We can use any radius server we like, and because we're using host APD, which I'll talk about in a second, there's about over 25 different EAP methods that we can use. So username, passwords, certificates, one-time passwords, and whatnot. And our system is fail secure. So this is just the basic network diagram we have. So up the top right, we have Faucet, and you notice it has a blue link, which is a link to a host APD. And then we have a red link Faucet to the switch, which is our control plane network. Our link to host APD can be connected via the switch if we want, or anywhere else, just as long as it can communicate and our ACLs are set up for it. It doesn't really matter where it belongs. I have it up connected directly. It just simplifies the ACLs. It makes life a little bit easier. Oops. Sorry. Wrong button. Okay. Then we have our network, which is where basically anything else on our network resides, our Active Directory, gateway, other servers, other switches, just anything. We then have our clients, which can be our Linux clients or Windows that both support 8021X. We then have our switch, which in most cases is probably going to be an OpenFlow switch. And then we have our host APD server. So host APD, you might have heard of it, you might not have. It's a host access point daemon, Linux user space application. Typically, it's used as an access point. It also has a 1X authenticator in it. It's very well tested and written, professionally used, I guess, widely used. And then we have our radius server. Why can't I go back? Whatever. So now we have our, from that diagram before, we have our supplicants, which are our clients, our host APD, which is our authenticator, and then our radius server, which is our authentication server. And our radius server can be connected anywhere on our network. I sort of assume that it's on the host APD server. Again, it simplifies my ACLs, but it can be anywhere we want. So we have three main processes in our system. We have host APD, and it's one sort of thing. AuthApp, which is my application, which handles the communication essentially between host APD and Faucet, and it also generates the rules that we want to apply. So host APD and AuthApp, they communicate via a Unix socket or a UDP socket, depending on if they're on the same machine or if it's over the network. So we receive messages from host APD on this when the client state has changed. So for example, logging on successfully or logging off. We can also in the future potentially add a few other ones, such as timeouts to handle different kind of conditions on our network. And then when we want to know more information about our client, for example, when we log on, we can then query it back by that same socket. So for example, we need our username, not username, password, our username, and we also want our ACLs. So between AuthApp and Faucet, we talk to Faucet via a config file when we want it to do something, and then send the SIG-hub. And then when we want to get something from Faucet, for example, the Mac learning table of where each user is located on our network, we use the Prometheus interface. So just going a little bit deeper into how we actually do things. So our client is going to send a 1X packet in this case to our host APD server essentially. So it's going to be from the client. It's going to be using the reserved MAC address for 1X traffic, and Ethernet type's going to be the 1X or EAPOL. That's going to be sent to Faucet, And what we want to do on the switch is, force it to the switch. What we want to be able to do is we want to be able to process it through the normal pipeline. So that allows our host APD server to be located anywhere on the network. And we don't need to hard code that in at configuration time, right? Or it can move around if it wants, if a link goes down or whatever. That's sort of the general idea for that. Right, so we have our ACL table, which changes the MAC address of our 1x traffic to be that of host APD. And that allows the client to be learned and which port they're on for the return traffic. I'm going to skip ahead to the slide and then go back. I can't go back. So once we receive, the host APD server receives that traffic, it's going to then reply with another 1x packet. And this is a reasonably simple case, so it's going to be destined to our client, it's going to be 1x. And it's just going to hit the normal faucet pipeline. There's no special rules for traffic in this direction. And it's going to get sent to the client. Can I go back? Yes, I can. Cool. And in other cases where traffic that is from a client who is unauthenticated, right? So in this example, I think I'm using DHCP. This can be ARP or TCP if they've already got an IP address. So it's going to be sent to the broadcast address. And in this case, we don't want this traffic to go out to anywhere else on the network, right? So what we do, so the client sends their packet to the broadcast address. We have a rule on our switch that says redirect, essentially says redirect all unauthenticated traffic to our host APD server, right? So we change the MAC address and it passes through the normal faucet pipeline and gets sent out to our host APD server and only our host APD server. Yeah, on that side. I don't think anyone's talked about like ACLs too much. So that's just a normal faucet ACL, right? So essentially we have a group of matches and a group of actions. So we can change our Ethernet header, we can match on our Ethernet header, IP, TCP ports and whatnot. And in our actions we can drop things, allow, redirect it, etc., and then change some of our headers as well. So that's just two simple examples of blocking SMTP for IPv4 and IPv6, which IPv6 has been dropped off. And then again, this is just so this is a bit of an example from the demo that I'll sort of show you in a bit. So we have 4 ports. You can't see the 4th one, unfortunately. We have port 1, which is our network, and that doesn't have any ACLs on it. We then have port 2 and port 3, which are where our hosts are going to reside. And they both have a unique ACL, port faucet 1.3 and port faucet 1.4. So that's just the port, and then the switch name, and then the port number, which just uses a unique identifier to identify each port that 1x authentication is going to occur on. Yeah. So this is just standard faucet stuff so far. Just skipping a little bit ahead. So we have these different files, and essentially what we want at the end of the system is to have an ACL that, a configuration that faucet can read, right? Over on the far right. So at the top here we have radius. So that we get our the ACL list of ACL names that we want to apply to our network from radius via host APD. We then have this base ACL YAML file, which is where our base configuration of our network that the 1x application requires for everything to operate successfully. I think I'll go back into this in a second, a bit deeper. And then we have this rules YAML file, which is where our rules from radius are generated for each user that is authenticating. So we can have different, that's where all the different ACLs are defined that we'll be then grabbing. And this is then converted into this base ACL file. This base ACL file has some extra state and whatnot. I'll talk about in a second. And then that's stripped out for our faucet ACL files, which then is given to faucet. So we have a vendor-specific radius attribute, faucet ACL names, which is basically a list of ACL names that we're going to apply. I think you're limited to 255 characters. Could be wrong on that. Could be 4096 or something. I'm not 100% sure. And then, so essentially, so at this point, our lists can be either like multiple items, right? Or we could have a single item if our radius server doesn't want to, I'm not sure the word is. So what we can do is we can build our ACLs from our rules file instead of having individual. So for example, I guess this example is, you could populate the faucet ACL names attribute via like filter ID or a VLAN and radius. If you don't want to specify that a specific ACL or series of ACLs in your radius server, it's up to you. Right, so this is, sorry guys. Okay. So this is the rules YAML file, which you cannot see. I wonder if I can. I'll show you an example later on. I've got the content file. So what is essentially the same thing, right? We've still got our usual matches, usual actions. However, we allow the use of inserting a username or MAC address at runtime, right? So we can specify which rule belongs to who later on in our base ACL file. We also have two types of rules. We can mark a rule with we can apply the rules to two types of rules, or ACLs. One can be the port that you authenticated on, or we can specify any other ACL that is going to be in the faucet configuration to apply it anywhere on our network, right? So if I log on port like here, I can apply rules here, or I could also apply rules, say, on some other port. Maybe there's a server that I'm not usually allowed access to, or normal users are allowed access to. I can change anywhere on the network if I wish, by specifying it directly by name. And some animations. Yeah, so this is our base ACL file, right? So again, it's pretty much the same as a faucet, except I've added a couple of extensions. First is auth rules, which I don't with a pointer. This auth rules here, so that's just a marker of where we can insert rules when someone's authenticated. And then we've also, this isn't going to work. Ah, it's not. Maybe I didn't have one then. And then we can also have, we can also reference by YAML anchors. So we can have, so say we have like, so we have some rules which are always the same between different ports. We can just specify that rule once and then use it by reference it by name in our ACL list here. Unfortunately, I don't have. Our system is sort of designed to be fail secure, I guess you call it. Yeah. So if faucet were to crash for whatever reason, or the system, the machine it was on, our rules should stay the same on our switch until the Ethernet tables time out, however, although you can change that by increasing the timeout length. And then once faucet boots up, you'll then apply the same configuration again, and it'll be all good. So yeah, so we shouldn't be allowing any other traffic through while the system's down, right? On AuthApp, same thing again. If it crashes, it's not going to affect faucet at all. As far as faucet's concerned, there's going to be no new configuration changes, so that's fine. And once that boots up, we can either do two things, right? We can reset you to the original state of no one being authenticated, or we can apply the last known good configuration, depending on what you want. And if our switch crashes, well, then nothing should happen until faucet boots up, and your faucet will apply that same configuration again. Yeah. So this is just a picture of the demo, which I'm not going to be able to show you fully. So we have faucet in a Docker container, we have host IP in our Docker container, free radius in our Docker container. They're all connected up to each other. And then we have our mini-net network, ransom hosts, and a network, which is just another host. And so in this picture, unfortunately, it's not interactive. So host 0 is not logged on, and then our pings here are not going through. And then host 0 has logged on, and our pings start going through, right? What you'd expect. Host 0 then logs off, and our pings stop. That sort of shows you. Okay. And maybe 1 second.
So you have this on your laptop as well. So if people want to do it during break as well. It's good.
I lost my mouse. Oh, that's the background, you idiot. Sorry. Can I open that? Oh, cool. Is there any questions? Yeah. Okay, cool. So, and it's not highlighted. That's fine. So here we have, oh, that's fine. Yeah, so here we have our pings not going through. So we're sending out some ARP requests. If I click on here, we're sending out source switch 1 Ethernet 2, which is one of our hosts. And then we're sending, and you notice it's a broadcast. And then once it's gone through the switch onto this link here, which is our Docker container link, we're changing our MAC address to that of host APD. And again, if we see down here, that's just going to be from our host APD server. Actually, no, it's not. This is from our client, which is fine. It's getting redirected. Oh yeah, sorry, I'm missing that one. So we have a pair of rules, pair of packets from Ethernet 2 to our Docker container. And that should only be getting sent out to one port, which I think is right. And then once we've successfully authenticated, we then have this rule here, the rule packet, and it's getting sent from our host, and then it's getting broadcasted out each individual port, because we don't know where this host is at this stage. At which point our internet host, which is on Ethernet 1, is going to send out a reply. And we haven't changed any MAC addresses here. And then when we log off, we have the 1x log off is then redirected to our host APD server, and our pings stop going through. F2, Docker, F2, Docker, F2, Docker, etc.
It's one of the main things that I love about your work here is like if host APD were ever to have a bug, which of course would never happen, then because of course it's no longer on the switch, that's just a Docker upgrade.
Yeah. Yeah.
It's really nice.
Didn't we? Oh, right. I think I lost slide. If I can find it. Future work. Link state events. So we're handling when link goes down. We probably want to de-authenticate or get everyone else to re-authenticate on that port, so you can't plug yourself in, change your MAC address, etc. A bit more flexibility, in particular those hard-coded port ACL names. Ideally, they'll be looked up from a configuration file, and then which will come in pretty handy for like Wi-Fi. We want to authenticate over many ports in just the once. Radius counting, so we can provide our whole AAA. Oh yeah, single authentication server for many switches. So have one host APD instance manage a stack of FAUCET, a stack of switches, because the load on host APD is not very big, so that's cool. Packet fence, which is a network access control system. which can provide 1x and captive port and whatnot for a wide variety of switches. So that'd be pretty cool to have configuration for that. I think having MaxSec would be awesome. I think it's kind of limited. We'll talk about that later if you want. And then some richer ACLs. Victoria University is working on a policy language to, I guess, control and look after your network. Thanks Google for your sponsorship, support. And if anyone's interested, we've got HostAPD. HostAPD is currently not the master version. I've found a couple of bugs with their control interface, so I've had to change them. Hopefully they'll get accepted upstream. And then I've also added support for retrieving radius attributes from the access accept message and sending them back via the control interface. So you'd have to use that one. And then if you really want, you can look at Radius ACL's branch of my GitHub repo. Is there any questions? Oh, yeah.
So if I understood your earlier slides right, when ACLs are applied, which is essentially when the authentication becomes part of the FAUCET environment, that is tied both to the authenticated source MAC address host, as well as the particular port in which it was authenticated.
Yeah, it can be.
Okay, so that second part is interesting to me because I'm wondering how you manage to maintain that information through HostAPD, which I presume doesn't actually bother to care about which port is in.
No, yeah, so in the Mac rewrite one, HostAPD doesn't keep that state for us, right? Because as far as HostAPD is concerned, the authentication happened on one port, which is the port that is connected to the switch, right? So if we, I don't want to open that up, sorry. So we grab the MAC address and the port from FAUCET itself. We grab that by the Prometheus interface. So that's how we grab that. But with the tying it to the MAC address, that's up to your rules that we define in the rules that YAML file. If you want to specify the MAC address of some other user for some other Mac for some bizarre reason, then I'm not going to stop you doing it. And then the off port part, you don't have to specify the off port. It can happen on any port that you like. If that gives you some flexibility, then yay.
So I think the idea of decoupling the user port from the authentication by actually having that ACL match on MAC address only might be interesting, where your control point is at an aggregation point, a choke point, not actually right at the edge of the network. Would that make sense in the way that you've architected this?
So your control point could be it could be at the edge if you wanted by the off port, or it could be anywhere else on the network, I guess. If you configured it like so. So you could have a dumb switch or a switch that had VLANs or something connected to your OpenFlow port, maybe like 5 high. So just have a single OpenFlow port, OpenFlow switch, and that would be fine as far as our system cares. I'm not sure that answers.
Yeah, thank you.
Great, well done. Thank you.
I'm not going to touch it. Oh, is that Trunk's phone? Oh, that's Trunk's phone. That makes sense. It was ringing. I want to log out of that actually. So I'm going to log out of my email account. Your phone rang. Well done. Sorry. Yeah.
That's so weird. This doesn't.
Maybe I got the wrong resolution.
Maybe
it didn't auto